So we'll be streaming it. It's working now. So theoretically, people could ask questions. But I don't think anyone's watching it, so.
Bigger?
Oh, there you go.
Yeah, okay. I thought it was.
So what was the problem?
Lyman-alpha.
No. Issue with the science.
I actually switched it to PDF.
Sorry, what is it? Oops. Yeah, it's the red button.
Yeah.
Okay.
I won't punch anymore. Thank you.
This is just for the recording.
Did anybody ever actually watch it online?
I think there was one talk where we had people online. Someone who got us.
There were questions.
From the distant audiences.
I would recall Neil was asking questions from cyberspace.
So how's everyone? You guys are the only one in town.
No, there's a few more. But people are.
Well, if you come to Berkeley, you'll realize most of us is out. Nobody. Yeah, that probably get most of the people.
Well, more than one the Great Lake Conference.
And the Great Lake Conference. Yeah, I heard about it. Well, it's the 1 week that I found between traveling schedule works.
So were you going around this year? No.
Yeah. I'm actually going to Pittsburgh after this, and then Aspen. So go back to California. So full loop.
Right.
Yeah.
Nice.
Hey, Ted. If you find anything wrong, you can't say it right away. I'm kidding. So there are more experts here than mostly anywhere else, I think. With you on Lyman-alpha and Neil's on FNL, yeah, I pretty much cover all grounds on this talk. Cool. So one reason I came here was that 2 years ago, I think I came here and gave a horrible talk. It was one of my first few talks in public. And so I hopefully will do it a little bit better.
Is this online already?
I think so. I just signed off my rights. Oh, also for people who want to visit Berkeley, I also help organizing the talks. So just email me. We can start. We don't have to wait for them. Oh, actually, we are early. Okay. About 2 minutes. So I don't know a bunch of the people here. I only know you two. Maybe I should just... Shirley.
Postdoc here.
Oh, what's your name?
Bridget.
Bridget? Ah, I know another Bridget in JPO. Cool. I know this guy. I don't need to introduce. I'm Shirley.
Hi, Morris Clement.
Nice to meet you. Oh, cool.
Hi, I'm Joe. I'm actually at chemistry. So.
Cool. You like Lyman-alpha forest? Cool.
Sorry, I forgot to send you my code. Oh, no, it's okay. Yes.
You coming to dinner?
Sorry?
You coming to dinner?
Where are you going?
We don't know yet. I was just going to tell you something more about what we talked about yesterday.
Are you doing your talk?
Not during the talk. That's too much details.
Oh, but this is not for dinner.
My host is not here yet, so.
And he said he would probably replace.
Okay.
Yeah. This might be it because you are. Good. Okay. So today we have Shirley. She introduced herself already, but she was
Know my name.
at the University of California, Berkeley, and then moved to Princeton, working with David Sperlo and Urosh, and also Chrissy Rother in Stanford.
I'm still working with the same people, not moving on too much apparently.
So now she's back in Berkeley, and she's going to tell us about Lyman-alpha course.
Yeah. Thank you for the introduction. So it's not because I'm working with the same people over and over again, it's because they're moving along with me. So Urosh was in Princeton when I was working with him as an undergraduate and then as a grad student in Princeton. But then he moved to Berkeley when I moved there as a postdoc. So there's a lot of looping back and forth. And Martin was my undergrad advisor. And then now I'm back to Berkeley. So it's a lot of interloopings, interlopers, whatever you call it. Anyway, so my collaborators, important collaborators, are all named here. So Anjay, Martin, Urosh, Vincent Jack, and Thibault Louis, who's actually an exchange student for like half a year with us, and we work together too. So today I'm going to talk about Lyman-alpha forest, friend or foe. I'll be concentrating on two effects that people didn't talk about Lyman-alpha forest until recently, and I will talk about them quickly. First of all, let's just talk about the outline a little bit. We have motivations. We have the introduction, what is Lyman-alpha forest. I'll be stepping through these one by one as highlighted by the blue color. And the two effects I just mentioned earlier is the baroacoustic oscillations, and hopefully you can detect dark energy at high redshift using this method, and also using scale-dependent bias, and hopefully do something with something called primordial non-gaussianities. I know these are not really names we throw around every day, so I'll explain what these are as I go along in the talk, and I'll conclude in the end. So the motivations, everyone knows what we're talking about here, but I just like to go back a little bit and say why we are sitting here in the summertime and not walk around in the city of Toronto, which is beautiful. I just did in the morning. It's a really nice city. First of all, Big Bang, Planck era, everything happened, and as humans observed from the lower redshift, time goes this way, redshift is going this way, humans right there. We observed movements of galaxies, and also we assume that we understand gravity because of Einstein, and we see something called dark matter, or we don't see them, but we think that they exist. And then distant supernova, these exploding stars, actually appear to be fainter than expected in 1998. And universe is probably accelerating according to this evidence in 1998 already, and people had talked about cosmological constants, dark energy. We have no idea what they are. And observations of galaxies cluster, cosmic microwave background, basically all these things come together and give us this picture that everyone probably seen it many times. Dark energy is about 70% of the universe, dark matter, and I always told my chemist friends they only study 4% of what I study. And I also add an extra question here is what happened at the very beginning of the universe at such high energy, what actually happened? So these three questions, that will be what I'm trying to hopefully stimulate some discussion of how we can detect or understand what happened to dark energy, what happened at the beginning of the universe. Okay, so I promised earlier to explain a little bit about non-gaussianities. What is the primordial non-gaussianities we were talking about earlier? I'm no expert in the theory of primordial non-gaussianities, but all I actually need to know for someone who's trying to detect it is to say that there is this primordial potential of the universe, and then we have something that's assumed to be just Gaussian random fields. And what people were doing is just go one order higher and say, what if we have a phi squared term? And that FNL, this parameter will come up again and again in this talk, will be parameterizing how much phi squared contribution are there to the primordial potential wells. That's all it is. And the simpler idea is to look at different inflation models actually give you different FNL parameters. So all the different inflationary models, such as the usual single field canonical inflation, will give you about FNL 0.05, and then you have dBi inflation, all these different inflationary models that will give you from 0.1 to 100, curvature models, and say Gauss inflation. So these are different experts that you should go look at their paper, but not to me. But basically the idea is that if you understand what FNL should be, then you can have a sense of what set of inflationary models, what happened at the very beginning of the universe, should happen. That's all. So this is a plot, x-axis for FNL. Y-axis is a bunch of different large-scale structure probes that we use to try to measure this parameter we just talked about earlier. This is FNL parameter. You can see the scale is actually really huge, from 0 to 400. And I labeled canonical inflation, curvature models, Gauss inflation are all within sort of what we've been detecting, basically. This is the first time people even try to use large-scale structure to detect FNL. Just one more side note. FNL, this model here, is actually the local model, which is basically coming from sort of like a 2-point function. That's why, well, I shouldn't say 2-point function, it's a squeeze triangle configuration, which kind of squeeze the triangle, kind of make it from 3-point to 2-point. That's why these are all more or less a 2-point or Pau spectrum correlation function. And what we did is that we took Sloan, photometric luminous red galaxy, that's the constraint we had, spectroscopic luminous red galaxy, the red dot is the detection, well, detection depending on how you define it, and there's the 1-2 sigma error bar and the 3 sigma error bar. The best current CMB measurement, depending who you talk to, is about this size. So you can see that the large-scale structure is actually comparable in some sense in the FNL local models in understanding what is this number should be, and thus hopefully telling us something about primordial non-gaussianities, what happened at the very early universe.
It's also probably competitive, for other types of spectra as well. Not all of them.
Not all of them. I'm only talking about local today, so I'm not sure. Yeah.
Like folded, for example, is also more competitive.
I don't know the answer to this, but you know this better. The next thing is, as we talked about all this stuff that we should be talking about Lyman-alpha force, right? What is Lyman-alpha force? That's the first question. And this has been this would be a difficult topic if I try to tell you exactly what happens, but you should ask Pet if you don't know or you don't understand what I'm saying, unless, well, I hopefully try to explain more as I go along. Going back to this picture, this is at the beginning of the universe, way here. These are artistic conception of what quasars are supposed to be. They're just lights coming through us, and as they go through all this gas and stuff to us, this is a telescope we're observing from ground, and that's a quasar spectrum with all these emission lines. What happened is there are a lot of interactions of the photons with the quasars, the quasar photons with the gas. And a pictorial version is if you take one of these emission lines, that's still the emission lines here, but then if there's an absorbing cloud, it absorbs, right? So that's one cloud. But then if they have a lot of absorbing clouds, then you have this forest of absorption lines. And that's why we call it Lyman-alpha forest, because this absorption line is actually Lyman-alpha line in the rest frame of that particular absorbing cloud as it sees the photon coming into us. So that's actually what it looks like with all these absorbing clouds. And a better picture of this is an actual Bose spectra. This is real.
Yeah, it's just funny, right? So your slides are like the compound slide, right? It's just images everywhere.
And anyway, this is one of the first few spectra from Bose at the very, very beginning of the survey, which started just last summer. So I think this might be, I don't know if people can remember it, but it's actually one of the first few weak spectra that we got. And you can see this is the Lyman-alpha line for the quasar itself. And these are the absorbing clouds that's absorbing it along the lines of sight from us and in between us and the quasar. All these little dips here are these absorbing materials. And that's where the Lyman-alpha forest is. And all I was trying to say here is that it locates the neutral hydrogen of the universe and thus sort of the undress densities of the universe. Okay, so the next thing is, what can you actually do with this Lyman-alpha force we just talked about and that Boss is detecting? I'll explain what Boss is a little bit later. It's an experiment that I'm working on with a lot of people even here, actually. The first thing is baroacoustic oscillations, and I'll explain what that is too. And hopefully we'll detect something called dark energy with baroacoustic oscillations of Lyman-alpha force. What are baroacoustic oscillations? So if we remember universe at 300,000 years old as a CMB courtesy slide from David Schlegel, all these little fluctuations that we've seen from the CMB basically grow into much bigger fluctuations today. And all we're using is these fluctuations as a standard ruler to basically pin down what dark energy is. Daniel Eisenstein et al. 2005 with the Sloan 2 and Sloan 1 people has actually detected this with galaxies. So this is y-axis is r squared, r being the distances, the co-moving distances, times the correlation function r. And then the x-axis is the r, basically just the co-moving distances. And what it's saying is that there is an extra power, sort of, at about 100 megaparsec over H, and there's just more galaxies tend to lie at that distance away from each other. That's basically what this bump is showing. Nikhil Pimanabam also has done this with photometric luminous red galaxies 2006. It's a little hard to make out exactly what happened here, but it is in the Fourier space, so it's a little bit harder to see because you have more bumps instead of just one bump, which is easier to look at. The question here is, if we don't use these galaxies, that will actually give you this bump, and we use Lyman-alpha forest, what actually happened? Since we didn't have data 2008, 2009 we started having data, we actually need to use the simulations. So here is shown a dark matter simulation that we got from Warren White. What we did is that, these are these parameters for the simulations. Pretty big box, pretty okay grid size. Then we apply something called fluctuating Peterson approximation, which basically just maps the overdensity of the universe to optical depth, tau, that everyone kind of familiar with. And then we say the flux, those little dips that we see, is just exponential minus tau, the usual formula that we had. The only thing that's different from what we usually understand is that this flux is tracing the overdensity with this function with exponential on top of it. Okay, so that's the skewards of neutral hydrogen. I guess everyone had lunch, so nobody's laughing. I was hoping to see from this line of sight, we see a lot of skewers of neutral hydrogen. Just each one of them, instead of kebab, you can actually think of a neutral hydrogen clouds along lines of sight. To be more exact or correct, we actually don't think about it as just absorbing cloud individually, but more as a temperature field or flux field that's fluctuating. But just for illustration purposes, each one of them could be a neutral hydrogen blob between the quasar and us. Well, what do? We have all these neutral hydrogen blobs that we can do something about it. And hopefully we'll detect the little bump that we were talking about earlier from Eisenstein et al. 2005. But before we do that, we actually had to check our resolution of the simulations. Does it make a difference if we use a worse resolution simulation? So we check the resolution 4 times worse, 2 times worse. The most important thing is that we don't see a bump at about 100 megaparsec over H. And if it doesn't add a scale dependence at that range, then it's okay. So finally, we're taking the correlation. Remember what we saw earlier, that little bump from the luminous red galaxies, all these red dead galaxies? So it has 3,000 cube, and it's 1.5 gigaparsec cube box.
Okay, so you're nowhere near the gene scale on this, right?
No, this one we're nowhere near the gene scale, but Warren White had done a much better simulation with the Los Alamos group, and they published a paper about half a year after this that actually had resolved the gene scale, more or less. with dark matter simulations. Gene scale for dark matter simulations. No hydro, no radiative transfer.
But not much changes though.
Not much changes in terms of the BAO stuff. There's you actually can reproduce the PDF of the fluxes and the 1D power spectrum using what Martin's simulation did, and also the BAO scale at the same time. While in this simulation, you cannot really reproduce the flux PDF or the 1D power spectrum that well. While his stuff actually does the whole range. Flux PDF, 1D power spectrum, and the 3D correlation function.
From PAO, changing the resolution, as long as it's that small, just change
It's so far away. Yeah.
So, the scales of the lower scale.
Yeah. Just the large scale, small scale, the split background split argument which you used to. So, yeah. Okay, but not to delay too much further, if we remember this bump here, and we just took the correlation function of those skewers we had earlier, we basically see this. Same kind of bump, slightly different. It's not too different. We have shown the red points here being the real space correlation function, while the blue crosses are the redshift space correlation functions. And this is using something called big boss density quasars. I'll explain what big boss is a little bit later. It's another experiment that has higher density of quasars than boss, which is currently running. A better picture. You can see that the y-axis is the same y-axis we talked about, r squared times the correlation function. Our x-axis is just the co-moving distances. You can see the bump at about the right scale that you expect also.
Why are the errors so much larger in redshift space?
Why the error is so much larger? Good point. I actually don't know the answer to that particular question. It shouldn't.
Optimal analysis.
So these are all just box-to-box scatter, and it's intrinsically all correlated with each other. So I wonder if there's some small-scale stuff that. How do you average the radial average it? This is the monopole. So this is just the monopole. We didn't actually have the 1 plus 2 over 3 beta plus 1 over 5 betas squared. Well, we should.
Larger because you're sort of averaging in different amplitude measurements, which for a Gaussian field, if you correct for that, you should get the same errors, but once you tilt them, you're dominated by only a fraction of the modes that are boosted.
That might be. That's why I was trying to say that all these error bars were sort of correlated, because these are just box-to-box scatter, and it's a correlation function. So all the small-scale stuff that can be boosted can be all linked back. Okay.
Even for just a straight 3D field,
Mm-hmm.
Fourier space, if you average modes that don't have the same amplitude into a
That might have problems, yeah. But yeah, we can check this a little bit more carefully. But these are just scatter, box-to-box scatter, so it had nothing to do with real error bars we're actually going to get. I mean, some intrinsic box-to-box scatter. We don't know.
It's the same boxes you're doing the same.
Exactly. But there's a lot more error bar that will actually go into this. I think there's a lot of systematics that we actually will have to worry about.
How many boxes do you have?
This one we have 5 or 8, I forgot. It's some number that's not very large.
I just wouldn't blow this off. I mean, it's a pretty big difference that.
I'm not blowing this off. I'm just saying I don't know exactly why the error bar is larger. Okay. But anyway, let's keep going. This is spreading out the little bump earlier and spread it in 2D. So as we see this ridge here, this shell, this is our perpendicular to line of sight, and that's our parallel to line of sight. And that's what we're showing here. It's just spreading the bump earlier into 2D direction, well, into this 2D field. And that's, you can see the BAO feature. We actually just take the matter density and do the BAO, just take the correlation function. That's what we see. That's the flux field. So all this picture is trying to convince you is that the flux field kind of traces the matter quite well, as you can see. This one is actually showing you what the redshift space correlation function looks like. in the matter correlation and the flux field. And you can see that they're actually quite similar, at least the shape-wise. The amplitudes are actually different from what you expect, but let me show you what happened next. So we think that it traces each other quite well, but there are subtleties here which I'm not going to talk too much about today. The first thing that we looked at is, are they tracing each other okay overall scale, especially the scale?
But the previous one thing. So this is the wedge-based correlation function, same as the previous block, but the R parallel is along the line of sight. And normally
Well, they're all the same, XY axis all the same.
sure, but it's meant to the R parallel has velocity term in it.
Exactly. You add the velocity into the field. That's all it is.
Compare this slide to the previous slide, and this is not the previous slide. Yeah. So what it looks to me visually, at least, which seems surprising to me, is that the opposite from what I would have expected. I would have expected that only along the vertical axis we get any change at all, whereas the horizontal axis would be unchanged. We got the opposite. But the vertical axis decreased, you should have increased, kind of like increases it, and the horizontal also changed. Now, how is that possible? Because
So we actually asked very similar question when we did this. This is actually something a lot of people had slight misconception on. There's a couple papers, so Martin White wrote a paper with Jordan Carson that actually even talked about specifically what these things actually change, how they should change even in this kind of plot for residual space distortions. And it's not what intuitively one would expect, which I actually thought so too. At first I think all the power would sort of go this side and then this the other way. But what I'm actually going to show you later is if we want to deal with this residual space distortion, we apply the simplest idea, which is just Kaiser. We just apply the Kaiser formula, take a theory shell, same R perpendicular, R parallel, take the theory shell. Nothing special. Apply Kaiser, which everyone knows how to do it. And that's actually, if I flip it in the right direction, as you've seen earlier, that's the theory one from just Kaiser. We're not inventing anything new here. We apply Kaiser to a shell, and that's what you get. And the left side is a simulations of the flux that we saw earlier, while the right side is just theory of Kaiser theory, nothing else. We didn't add anything extra to a shell, which is counterintuitive. I agree. I actually saw this and I'm like, why is it this way, not the other way around? I had the exact reaction actually. But Martin convinced us that it was supposed to be this way. And we see it from just applying Kaiser. Well, I say here we understand approximately how to deal with residual space distortions. But this is not entirely the whole story, because what I show you here is sort of the amplitude of the Kaiser effect is actually different from what you expect. So I had this long discussion with Pat that we came full circle to understand what he has done before. But I'm not going to talk too much about this today. The good thing is we think we understand approximately how to model residual space distortions, so we can go from this, we need to go from basically this plot that has residual space distortions in the flux field to the matter BAO field, right? So that's basically what we're trying to do in BOSS. Okay, next thing. Simple. What's Martin's argument? He actually just showed us the plot that he made like many years ago, and then that's that.
It's just that a radial mode attributes transverse correlation. A radial 4K correlation is adding transverse correlation. So, and that's what boosts the radial 4 mode. And they're boosted a lot very well if you have the bias.
So I have some mode oscillating this way. And you're saying this is boosting
The point here and a point transverse to your line of sight are completely correlated for that mode.
But then you consider modes.
Yeah, the transverse modes that aren't boosted actually are oscillating.
Okay, well, there's a lot of discussions we should talk more about, because I'll be visiting here for today and tomorrow. There's possible systematics that I want to go through this talk. There's a lot of stuff that we don't know what to do yet, and BOSS people are working really hard on this. The first thing we checked is UV background fluctuations. We would like to check the other stuff, such as metal line contamination, metal absorbing systems along lines of sight, many things that can contaminate this signal, because in particular, metals actually traces large-scale overdensity in some ways. Continuum subtraction is basically this continuum we're talking about when we see this Lyman-alpha forest, and you have these little dips, but you actually need to subtract the sort of the mean or the continuum over it to get the change of flux. And other IGM physics that we don't understand. Well, the only thing that the first thing we actually try is UV background fluctuations. We take the same box. What is UV background fluctuations, first of all? Is that if there is a lot of UV light coming out from one of those areas that we didn't expect, we didn't know there's a quasar, we didn't know there's a huge UV source there, it ionizes the region. And because of that, you can actually change whether, if I see there is a neutral hydrogen blob, but if I don't see it, does it mean that we actually just have a quasar nearby ionizing the region? So that's why we need to worry about this particular systematic called UV background fluctuations. It's very astrophysical. So what we did is that we take a dark matter simulation and drop a lot of quasars into this. This time randomly, but then the next time that actually Martin did, and actually Orochi and I did separately, is to actually trace the dark matter halos a little bit. But for this one, we actually just drop it in according to a luminosity function by Krum et al. 2004. That's the luminosity function. And what we did is that you take the luminosity of each quasar and you just say, okay, it's going to have this scale length that will actually drop off, sort of a Strawman sphere. And we take this scale length as 100 megaparsec over h, which hopefully will give us the worst case scenario because it has the same scale length as the BAO scale, the 100-ish megaparsec over h. And that's just the usual 1 over r squared. And that's the ionization background from each of the quasar. So we did that. And yes? Sorry, say that again? This is just randomly distributed in the box. But Martin and the Los Alamos group did actually trace the dark matter halos, put it in correctly. Orochi and I did it for a different reason, that we actually put it in also through the halos. It doesn't really change much. What happened next is that I'm going to show you the same plot we saw earlier, except here the UV background fluctuation is 0%, and here the UV background fluctuation is 20%. And you can see that the signal is actually changing from the upper left to down right, so increasing the signal strength while the UV background fluctuation strength along the way. There are two reasons that we shouldn't worry too much about this. One is that Jason Prochaska and Gaber, I forgot his last name, I'm feeling bad here, has realized that for a high redshift, the UV background fluctuation is about 5%, which is sort of this case. And the second thing is that you can imagine actually fitting this out. You can fit it with a Gaussian plus some kind of correlation functions plus a bias. Basically what it changes is bias and the width of the peak. So you can actually fit it out, hopefully, from this case and not changing the BAO signal too much. So what I'm going to talk about today for the BAO, hopefully summarizing quickly, is that we approximately understand how to model redshift space distortions and what happens when we include systematics such as UV background fluctuations. But what this is sort of a hopeful thought is that maybe BOSS, which I'm going to talk about what BOSS is, Lyman-alpha forest, will hopefully detect redshifts, at redshift larger than 2, the dark energy measurement, whatever it is, whether it exists or not. And big BOSS Lyman-alpha forest, which has 6 to 8 times is sort of optimistic, 6 to 8 times more quasars. Yeah, this number changes all the time. We'll make an even better measurement at redshift larger than 2. The reason I said the big BOSS number for quasar is changing all the time is because this is an experiment that's being proposed. So I quote the numbers from the white paper. No, it's not 50. It's more than that. So now we're having 15 per square degree in BOSS. So let's talk about what's BOSS. a little bit. I know Andre visited a while ago, so I might not talk too much about this. But basically, it's a working telescope on the old Sloan telescope. Well, it's a working experiment on old Sloan telescope at Apache Point. It's running. It has collected data. We have about 10,000 quasars right now. That's higher than redshift of 2.2. From the redshift 2.2 to redshift 3.5 approximately, that's the range we're aiming for to do Lyman-alpha forest. Of course, this is sort of the side project nearly. It's a piggyback project on top of the big luminous red galaxy spectroscopic survey, which will give us 1.5 million luminous red galaxies to redshift of 0.8. So basically take the old Sloan and make it spectroscopic. Old Sloan imaging and take it all spectroscopic. And the main science drive is to do baroacoustic oscillations with the luminous red galaxies that Daniel Eisenstein had done, which hopefully will give you a 1% measurement on all these D of A distance scales and thus dark energy. The Lyman-alpha forest part is what I just talked about. And hopefully we'll get 160,000 quasar. I will probably scale this a little bit smaller, but that's using only 20% of the fibers, and you might be able to make the first measurement of dark energy at redshift larger than 2. When you think about it, what other probe can measure dark energy, if it exists, at redshift larger than 2? Supernova hasn't pushed that far out. None of the tracers can actually have that number density that far out. So this is something high risk, maybe high return project that I would encourage everyone to think a little bit about. Big Boss, which I talked about earlier, about the density having more, I said 6 times quasar, more quasars here. It's supposed to get 50 million redshifts. So Pat is smiling here.
Do you know what the magnitude of it is?
It's all changing because they're trying to say they use a different CCD in like the red, and they're like making it, okay, sorry, this is very detailed, but let me go through this quickly. If this is surface of last scattering, we have the O Sloan, which is down here, and that's supposed to be Boss. And then all these skewers out here is sort of the Lyman-alpha forest skewers that comes out, all these little ones. And the big Boss, the galaxy, should be right around here. And we're supposed to get this huge number of redshifts from all these galaxies that are emission line galaxies mostly. Some of them will include the old luminous red galaxies population. And on top of that, have the emission line galaxies and the quasars going to just basically dimmer magnitudes limits. Huh?
Getting dimmer with time.
Well, so that actually, let's just address what Pat was just asking about. He was asking what kind of magnitude limit you have for the Big Boss experiment. So this experiment started off with a 2 weeks. We wrote a white paper and say, what can you do with BAO from ground? That's like a 2 weeks time scale. We wrote a white paper and say, okay, approximately that's what you can do. There's a lot of approximation and tutors in there. And what happened is that actually DOE did give us a first year funding to do research and development. And the CCD lab is supposed to make these magical CCDs, as I call, since I don't know how to make them thicker. So supposing you can push the magnitude limit down a lot more. That's something you should talk to Natalie Rowe, which I have no expertise in. However, there's a chance that you can actually do it from ground pretty nicely. At least that's the argument so far. Talk to David Schlegel, talk to people who knows about this. We're writing another proposal to hopefully put this on the NLAO telescope in about July. So there will be probably more proper understanding what this experiment could do from ground once that proposal is written. So you can, if interested, please look at the white paper and the web page. Yes?
You put it on the label, so the green thing goes out to 1.8. We're talking about
Mm-hmm.
And then what is that circle? What's the red circle?
I believe the red circles is probably, I don't actually, good point. I think the red circle is supposed to be between 1 and 2. So they might be hinting at something. So at some point, Adept was talking about.
That's not 2.5, so that's the yellow GZ.
Well,
The green is Big Boss. I mean, the green is Boss.
Yeah.
The red is Big Boss extending the luminous red
galaxies.
Maybe.
And then the blue.
Blue is the emission line galaxies at higher redshift, which is when it starts forming, and thus the 2.
2.5, and then the
No, that's the quasars, probably out to 2.5.
2.5.
Yeah, so this is 2.5 to 3.5.
1.8. So the outer edge of the blue circle is 1.8, is what we're saying.
Something or like 1 or 2-ish.
It's a J-down scale thing.
Yeah, so this is not existing yet. BOSS is actually working, so that's actually something we should keep in mind. We should work on BOSS, and maybe big BOSS will happen. Neil has a question. No? Okay. But yeah. The next thing, what time is it? Okay. So this is going to be pretty quick. Well, I talked about scale-dependent bias earlier, which I didn't actually explain what scale-dependent bias is. But we did talk about primordial non-gaussianities, which is what can tell you about inflationary scenarios, like what happened at the very, very beginning of the universe. Back to this plot we showed earlier, that's different large-scale structure probes. And just to show that we actually are sort of comparable with the CMB measurements with the large-scale structure probes. This plot is just explaining, this is not real, this is simulated. Well, actually theory. Power spectrum on the y-axis, K being the Fourier modes. And if you have two different tracer, one is, say, luminous red galaxy, the other one is just main galaxy, simple galaxies from Sloan. And if FNL, which is the parameter we mentioned earlier, is non-zero, you will have this extra large-scale power at the largest scale of what we can detect. And that's what I call it scale-dependent bias, because if you look at this line is scale dependence, depends on the K mode, which K you're talking about, which scale we're talking about. And that's, if you take this line and divide it by this line, which is sort of the fractional change due to the FNL parameter, which is what inflationary scenarios that might actually have happened. So what I'm going to talk about today is how to get that fractional change using Lyman-alpha forest, which Neil might disagree with me very quickly, but we'll talk about it later. This is a box, same simulation box. Well, this is actually a box from Ursch and Vincent Jack in Zurich, but same mechanism actually, it's very similar box. And we apply the fluctuating computers and approximation, same game, same drill, except this time we have primordial non-gaussianities in it at the very beginning of the box. And we have the skews, the neutral hydrogen, same thing, except I take the power spectrum of this box this time, not the correlation function. So instead of taking the configuration space correlation function, we take the Fourier space. And if we take the ratio of the dashed line to the ratio of the solid line, which shows you the fractional change, as I mentioned earlier, due to Lyman-alpha forest, that's actually what you get. Sorry for this, making these big dots just so that you can easily see it. I'm actually using big circles over the dots that we show in the plot itself. FNL equals to minus 100 goes this way. So you can see that it's about 30% change of the power spectrum at the largest scale, with only 1/10 of the big boss quasar density. So that's how many quasars we kind of put in the box. That's actually a theory prediction that Vincent Jack has rolled out. So he can actually write this out. This is not exactly tuned to exactly the same redshift yet. But for different redshift, you actually have different measurements. But we can see the proximate trend is similar. And the fact that FNL equals to minus 100 actually goes upward instead of downward, which is usually the case for galaxies and quasars, all these other probes that we used before. So the good thing is we can more or less predict it. The bad thing is, well, there's a lot of systematics we will talk about later. But the first thing, as we remember from BAO, is probably redshift space distortions. Can we deal with that?
So you're looking for an excess at small k, which
large scale
as a Poisson noise would do. Let's say you have, and you say you did it already, but I would have said that if you have a fluctuating UV background with a patchiness of order of 10⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻
So that's something we actually haven't checked, but we are trying to check it. So whether throwing in UV background fluctuations, how would it change things if we follow the halos itself?
Yes, but we know the answer, right? And the answer is that an add of sound noise equal to the number density of the sources. So if you want to add, let's say 10 to the minus 4.5, 10 to the 4.5 to your power, all you have to do is put on a population with the modulation of order unity at that scale, which is away from 20 megaparsecs.
It's not Poisson noise. It's Poisson noise modulated by 1 over R squared and also with a nice optical having created the Newton path. But it is going to look a lot like this. I'm not arguing with it at all with the fact that it's a big problem.
Yes, it looks the same.
It is going to be a problem, which...
It might look more like this even like Poisson.
So, but yes, we do think about this, and we haven't shown that plot.
So you were actually mentioning earlier that due to this UV background, the width of the correlation function and this stuff is changing, and that you were hoping to find some fitting formula to get that.
Exactly.
Are you actually doing this in
Well, we're trying to do the same thing. We haven't...
No, I mean, when you tried to get that function, did you look at it in the power spectrum? Because it's probably easier to find that, right?
So these two projects are actually at some point going on at the same time, but then we decided to finish the BAO paper first. So we did not actually look at the power spectrum space for that particular UV background fluctuation statistics.
That's one, I think one would expect, because all these width changes are just the very high K.
Yeah, it should be higher K. So, but that's a good point. We do think about it, and we haven't done it yet. But the first thing, easier thing to do is versus phase distortions, which we just plotted here. These lines are the versus phase distorted parameter. So the cool thing is we actually believe right now we can actually predict what happened in the versus phase distortions also with the FNL parameter, which is cool. But there are a lot of things to work on, as you mentioned just now. There is the versus phase distortion effects, the effects of DLAs, BALs, all these other stuff that we don't understand very well, the metals. Incomplete continuum subtraction might actually also cause some problems, maybe not. The other systematics, like the UV background fluctuations, might matter too. But if it's really fluctuating by 5%, which is what people see, then maybe it's okay. That's actually why I didn't put it higher up on my list of things to do.
But the fact that that has to be density, right? So the order unity for 20 megaparsecs separated is the same as the 5% at 100 megaparsecs. I mean,
Yeah.
it's a product that matters.
I have to think a little bit more about this. But this is, of course, a paper in work, and the BAO paper is out, so please feel free to read it. Conclusion, we have Lyman-alpha force in BOSS and big BOSS, which might happen. We'll hopefully do the following, which is using BAO to measure dark energy at redshift larger than 2, and probes non-gaussianities of early universe, which might tell us about inflation. And there are other applications such as, of course, the 1D power spectrum, which you have in-house expert here to tighten the cosmological constraints, such as neutrino masses and the slope of the power spectrum. The temperature density relation in the intergalactic medium. We have to remember here is that we have 160,000 lines of sight coming up with all these Lyman-alpha force. 160,000 is like unprecedented before. Unprecedented. So there's a lot of things we could do now that we cannot do before. And my personal favorite is to maybe use it to find missing barons at higher redshift. But talk to me about this if you want to know more. And I'll end here, and thank you, and I'll take questions. Or maybe they asked all the questions already.
Yeah, probably everybody wants to coffee upstairs. So yeah, then
We can move up.
Take